Thanks a lot. Hope you can see my screen already.
Yes, we're all good.
Perfect. So yeah, today I will be talking about similarity learning and how it might be used to improve the data quality, especially in case of images, because this is a computer vision meetup, right? But let's just start with, first things first, let me just introduce myself. My name is Kacper Łukawski, and I work as a developer advocate at Qdrant. Qdrant is an open source neural search engine. So in case you are looking for for a tool to support and approximate nearest neighbors, this is the first choice. I can strongly recommend. Here are my socials. If anybody want to stay in touch or just have some questions, please feel free to reach me out. And let me start with the general description of how we used neural networks for image classification back in the days. Because actually this is an important point if we want to talk about similarity learning. I used to assume that everybody knows what similarity learning is, but this assumption is terribly wrong. So we need to first try to describe the whole process and how it is different comparing to the traditional classification that we probably all know. So neural networks have been designed to solve classification problems and typically work in a similar way, no matter what kind of data type we are using. So here is a really small network that transforms given input images through some processing hidden layers and outputs the probability distribution over 6 classes. And this is how, in reality, neural networks will work if we wanted to perform classification on literally any kind of data. Those neural networks have a bunch of layers stacked on each other. And the last layer will typically use something like softmax activation function. So the output might be seen as some kind of probability distribution over classes. And the highest score wins. So in this case, the second class would be chosen as the most probable one. However, in similarity learning, we do a different thing. We strongly focus on those intermediate layers that are being used because we are interested in neural embeddings. And since each neural network is, in a nutshell, a series of stacked operations, mostly multiplications and some nonlinear transformations of the previous layer output, we can actually think of every single hidden layer as some sort of data representation, the representation of the original input of the network. And that actually means that we can see the input and output of each layer as some kind of embedding, some kind of different representation of that data. And we can also use that information for some comparisons between different data samples. And the temporary hidden state of a particular layer is typically called embedding or encoding. And that's, as already mentioned, a different data representation hopefully capturing some useful pieces of information. So that's something that we heavily rely on while working with similarity learning. Because if you have this original network designed for classification, we could actually get rid of the last classification layer and try to work with the state of the previous one. We can simply detach the output layer and start extracting this state as a representation of the input data. And it is no longer going to be a probability distribution over our original classes, but just some kind of, let's say, random numbers that are really hard to be interpreted. And this is often called encoding or embedding. And we hope that it should capture the properties of the original input objects, in this case, images. And thanks to the fixed dimensionality of this vector, because the dimensionality of that vector is equal to the number of neurons in a particular layer, We can also start comparing those vectors and use the distance between the vectors to determine if two objects are similar to each other. So in our case, if we put a different image as an input, we would expect to have a different representation. But if those images are similar to each other, those representations, though, and embeddings shouldn't be that far away from each other. And there are many pre-trained neural networks available for actually any type of data you would probably use. They are mostly working with textual data or with images. But if you just take a network which is trained on, let's say, ImageNet, that is a commonly used data set, there are high chances that it won't be able to be directly used on, let's say, medical images. Those layers should definitely capture some useful pieces of information because they will capture some kind of shapes, patterns, and colors that are being used on those original images. So some low-level traits of the pictures, those are pretty universal, right? But since the initial goal of that network was to classify the images, I mean, any kind of pre-trained model, the top layers will be mostly focused on classification. So if we want to use those previous layers as embeddings and want to compare them, then it may require some fine-tuning. So fine-tuning is a process of putting some extra knowledge into the already trained model. And this is fairly easy with neural networks. However, it may require a lot of computational power, and that incurs, of course, some cost-related things. This is also quite expensive. So not every single organization may afford training their models from scratch, especially those transformer-based models require a lot of computational power and a lot of GPUs to be trained. So the process that we can try to follow is the following one. Actually, there is no need to perform a full training of the neural network that we originally had, but instead we could just attach a new head layer at the end of the network and try to fine-tune only this newly attached layer. Since we believe that those previous ones are already encoding some useful signals in the input data, we just try to find a good projection to a different space, but only using the second last layer of the original network, since we removed the classification one. And if we attach this head layer and try the network again, I mean the full network again, that may cause some troubles, just because still it would require a lot of efforts to be done. So the idea is, if we just attach a new layer, we can just try to train only this one in a way that two objects which are similar in some way, no matter how we define that, will be close to each other in this embedding space, or the latent space. This is how we call it. And what's more, we can also freeze those original layers. So the only this newly attached layer will get its weights updated. And that's the thing. So effectively, we are not going to be training the whole model, but only a single layer. So a single projection with some nonlinear transformation included. That makes some boundaries, of course, because definitely we could expect some better results from a full training process of the whole network. However, if we just limit ourselves to train a single layer model, then it becomes way faster and still can give you some great results. There is only one problem with this setup. Since if you were working with classification problems, then you typically have some kind of ground truth labels. So creating those targets is really simple, because we can encode the target vectors to be like one-hot encodings of the classes over the classes vector. So with similarity learning, we try to train this model so it no longer produces this probability distribution, but instead it produces some kind of vector representation, some kind of embedding of the original data. But we want the model to be trained in such a way that two objects which are close to each other will have similar representation, and the similarity between them is calculated using some kind of distance function. Typically, it's Euclidean or cosine distance function. Those two are probably the most commonly used ones. So instead of providing the targets for the input samples, we provide the network with some similarity-related information. In other words, we say which objects are similar to each other and let the network select the embeddings in a way that similar points will be represented in a similar way. Without telling the exact coordinates, we do not know those perfect embeddings for given data. So the goal is just to adjust them in a way that they will be close to each other. And one thing I forgot to mention is how we train the network without in this limited process, without training those first layers, but just training the last one. Actually, if you look at this picture, you may simply see that this process, which is just transparent here, is deterministic, because if we freeze all those layers, then this transformation is deterministic. So for every single image, we can expect to have exactly the same output, because those parameters are not updated during the training phase. Only those ones are. So actually that process of training might be simplified a lot, because the forward pass through the network might be done just once for every single input image. And then we can just process all the embeddings or the original embeddings of that network through this additional layer and train only the simplified model. And in order to do that efficiently, we created a library which is called Quaternion, and Quaternion simplifies this kind of process. So if you want to use this setup and try to make this training, Quaternion is a way to go. It may simplify your process a lot. And there is also another thing. This original network is already capable of capturing some useful signals from the input data, because it is designed to work with images. We just want to change the output of that network, but not necessarily update those signals, so we do not lose some useful information. So the goal here is not to change those original embeddings into some completely new ones, but typically we want to slightly adjust the original embeddings and just move those numbers a little bit. So as you may see, there is not huge difference between each coordinate. And that's the expectation that I would have from those embeddings, because if we wanted to start with some random projection, then we can lose some information. And this is called catastrophic forgetting. This is it. This is how we train the network for similarity learning using those boundaries. Of course, we could train the whole one, but if we decide to use this setup, you can have a few hundreds faster training with still decent results achieved. And there are some different loss functions being used comparing to classification. Triplet loss is one of the examples, and for triplet loss, we need to provide some triplets. There is an anchor, there is a negative and positive example, and the goal of the learning process is to move those points into the latent space, adjust their coordinates, so the positive example is closer to the anchor than the negative one, keeping some margin in mind. And that's the whole process. We also built our data sets differently. Actually, one thing to mention, if you already have a classification data set, it's already prepared to be used for similarity learning. That's a good thing. because there are two ways how we can provide those samples into the network. The first one, based on classification data sets, objects that belong to the same category should be close to each other, and objects with different categories should be our negative examples in that case. That's not necessarily true in all the cases, because we can have some overlap between our classes, or the objects are quite similar. Let's say we want to determine some different brands of cars, maybe also some other attributes. Then it would work. But if you wanted to detect some species, then they might be quite similar to each other. But that's one way. And if you already have a classification data set, you can use it right away. But there is also another strategy. Instead of providing groups of samples, like in this case, we can also provide some pairs of samples with an additional piece of information, the similarity measure, the target similarity measure, typically a number from 0 to 1. 0 means there is no similarity. Those objects should be far away from each other in the embedding space, and 1 is a perfect match. So those objects represent samples represent the same object. And as I already said, if we decide to perform this fine-tuning of the network with those boundaries, so with freezing the original encoder and just attaching a new head layer, we can actually use very little data for training purposes. So we no longer need to provide millions of examples that are annotated, but instead we can focus on 1,000 or 10,000. So way lower number, and still fine-tune the network. And this amount of data might be probably annotated by a single person within a day or two. So that simplifies a lot if we start with pre-trained model and then fine-tune it for our purposes. But okay, I've already spoken about that vector search or similarity learning, but how is it related to data quality? Actually, since the goal of similarity learning is to find the proper representation of our input data, so similar objects are close to each other in this embedding space, there is also a distance function that has to be used to compare the similarity. Euclidean or cosine are great examples here. And that already gives us a great measure to determine if two points are not only close to each other, but if they represent some different objects, different concepts. And that brings us to the example. Let's say we run a business, we have a furniture web marketplace, and we have thousands of products, thousands of items, and every single item belongs to a category, to a specific category, possibly even multiple categories at once. And for sure, if we have lots of products, tracking the quality of that data, if the product is assigned to a proper category, may become hard. And at some point, we may decide to just automate that process to determine that maybe we need to create another category in our store just to have a better user experience, or simply sell a little more just because of wrong categories. We can lose some income just because people won't be looking for a specific item in a wrong category. So we want to automate the process, and we want to find the items which are assigned incorrectly with similarity learning. And there are various ways of how to do it. Of course, if we run a furniture marketplace, we are going to have some images of our products, but also their names and the category they belong to. And that gives us a great chance to perform this process of automated data quality check. So first of all, what we need to know, the model that I presented before, the simple neural network, was capable of encoding images into some vector space. But since we have some product names and their images, we need to go for multimodality. And multimodality means that we need to have a model which will be able to encode not only text, but also the images. And the good thing about that is that we can encode the text and image separately, and they will be converted into the same latent space. So as a result, we will be able to compare text with images. There are also some existing pre-trained models which are able to do that. A great example here is Clip. Clip is a model that is capable of encoding texts and images into the same latent embedding space. So this is pretty useful. And the basic approach that came to my mind was to just simply calculate the distance from every single product to every other one, and find those ones which are furthest from each other. And that could possibly work. But it seems like there are some better ways of how to do it. And there are a lot of different approaches of how to implement this quality check with similarity learning and those multimodal models. And we are going to go through some of the examples, but you can probably think about some different setups as well. So the first one, okay, what is the goal? We are going to be working with a specific category. In our case, this is going to be single bets data set. So we are focusing on a specific category. We have some objects that we know that are properly assigned to that category. But of course, in that category, there will be some outliers as well. So the basic setup, the basic idea is that we can take the name of that category as an anchor and calculate its embedding. So we are going to have an embedding of the single bets category name processed through the text encoder. And then we just need to calculate the embeddings of all the images from our data set and compare the embedding of the category with those embeddings of images, for example, because the problem may be not only related to incorrectly assigned items, but sometimes in this case, there are also some images with incorrect name being assigned to them. So somebody just made a mistake and put a wrong image to a correct product. That might be also confusing for our users if they have a different name and different image in the marketplace. So by creating this single text embedding from the category name and multiple image embeddings, we can just try to put them into the same space and try to figure out which are the furthest embeddings in that space comparing to the category embedding. We can just calculate a distance matrix. And by this means, we can simply calculate those ones and even sort them by this score. So that's one of the ideas of how to implement that. Maybe not the best one, but that already allows us to perform this quality check and find the outliers. Of course, that probably requires some kind of thresholding and cannot be fully automated because there might be an issue with our embeddings themselves, or there might be a broad category that just collects items which at first glance may be thought to be completely different. But this is like a basic setup that we could use. But another example is to combine this titles of the items that we already have with images for those items and simply take the mean of both embeddings which were created. We could also go for titles alone. That's also possible. But in this setup, since we are encoding the titles and images into the same vector space, we can easily add them and calculate the mean of them. And this is also quite often being done. And then we do exactly the same process. We put all the vectors, they are already in the embedding space, but we calculate the distance matrix between all those examples to the embedding of the category name, and try to find out the items which are the furthest ones. That also works, and from our experiment, it seems like this process is able to capture some different items than the previous one. So this is like a different method, and it allows us to find some more outliers. But there's also another concept I would like to share with you. It's called diversity search. And diversity search is actually a method of finding the most distinctive examples in the data. Well, it's based on similarity search, but so it also operates on embeddings and measures the distances between those embeddings. And here the difference is that we just decide differently of how to choose the next point to be extracted. But let me just go to the example right away. So in case of similarity search, we would calculate some distance matrix, we would choose the anchor for the comparison, and just, let's say, get top 3 embeddings which are the furthest ones from the selected anchor. But in case of diversity, we would just initialize with some random point in the space of embeddings, no matter how we calculate them. Let's say we will no longer calculate the embedding of the category name, but instead we are going to calculate the embeddings of images alone or images with their titles, and then start the lookup in this space without having any anchor. Because with diversity search, we are going to initialize with some kind of starting point that might be just selected randomly or using some heuristics with some conditions that has to be fulfilled. And then we need to get a distance vector from a selected point. So by taking the distance vector, we are going to find the furthest point from the given one. So this will be one of the items which might be thought as an outlier. And then we do the same process again. So starting from this point, we might be looking for the point which is the furthest one to each. So basically that allows us to traverse the space and find the examples which are different from the others. And that actually allows us to find the outliers in our data set. That might be thought as a valid method of finding those ones which should not be assigned to the category. Of course, with some human intervention in the loop, because if our data is of a perfect quality, then we won't be able to do that, and we are going to just recognize the product which are the most unique among the category. But still that's a way to improve the data quality, not only in case of marketplaces, but actually in any case that involves having huge amounts of image data. And of course, I was talking a lot about distances between points in the embedding space, and that wasn't a mistake. Actually, if you want to perform any kind of vector search in production, then you probably need to have a mature tool to do that. And nobody is going to convince you to build your own tool from scratch. There have been a lot of going on recently in terms of vector search. There are a lot of startups, and Qdrant is one of the open source vector databases that is written in Rust. It is based on HNSW graphs. It's a structure that is quite commonly used to perform approximate nearest neighbors, because that's, in a nutshell, the thing that we want to perform while looking for the most similar entries. But we have some tweaks incorporated into this algorithm, so this is not the pure version of it. So we allow to filter not only by the distance of the points to find the closest one but also if we want to filter items, let's say items or objects belonging to a specific category or having a specific value of a different metadata attribute, you can also do it, and this is done directly in the filtering phase. This is quite unique approach that nobody else is using nowadays, I think. And it can be launched with Docker or Kubernetes, no matter how you prefer. There's also a Qdrant cloud currently in beta, but if you want to try it out, I really encourage you to go to our website. There is a link to a form when you can just apply for the access to the cloud version. And that would be it. Thank you very much. If you have any other questions, please feel free to reach me out. There's our email address, a link to our website, Discord community, and do not forget to give us a GitHub star. I think that Qdrant really deserves that. And would be happy to answer your questions if there are any.
Yeah, Kacper, so if you click on over to the Q&A widget, it looks like there are 4 questions. A few were answered in chat, but Michelle has brought them over, so all your open questions should be in
cool.
Q&A.
Okay, hi, can you please elaborate on differences between fine-tuning the last layer and performing a clustering on embedding space based on distance? Actually, that's the same process. There are 2 things. First of all, if you just take a pre-trained model, let's say trained or ImageNet, and you want to use it in a different domain, then those original embeddings won't be probably able to capture the similarities between those objects that well. So the goal of fine-tuning the last layer is to just adjust the original embeddings, in a way that those similar points will be closer to each other than they originally were. And comparing the distance could be actually done on those original embeddings, but in reality, that is not the they do not provide the best quality possible out of the box. So this was like an approach to fine-tuning, and comparing the embeddings is done just right after this process. Okay, what are the advantages of similarity learning by looking at the embedding space rather than define a classification after softmax? Is it to save computational time because you don't need as deep layers? How many layers can it save? Is similarity learning compatible with transfer learning using pre-trained models? In that case, all the layers are frozen and don't require training and can save computational time. I may not understand similarity learning, but okay. So first of all, you could probably use the final outputs of that network, but since it was done to solve some kind of classification problem, those vectors would typically have a one, or not typically, but basically they won't be capturing the regularities that you have in your data, in your images, but instead they will be trying to model the probability distribution of your classes. And since we are not trying to solve the classification problem of that the pre-trained model was trained for, instead we want to compare, let's say, the content of the image, what it represents, and those kind of things. Those previous layers will typically have some sort of well, let me if you have some experience with NLP, we've been using sparse vectors to represent the content of the text, and we still do, but these vector representations are of a lower dimensionality, and they have some this is like a different data representation. That's the thing. The classification layer could be probably used, but in reality, since we are not solving the problem of classification, those previous layers work a bit better. Still, that's a challenge to choose which layer to select, but it is not about saving computational time, because this is just a single layer being removed. But when it comes to similarity learning, this is transfer learning in a nutshell. We just take an existing model and apply it to a different domain. So basically, that's exactly transfer learning. The only difference here is, well, actually, that's not a difference. But if you have an existing model trained for, let's say, 1,000 classes, and in your case, you want to recognize some different classes, you would still need to remove the last layer, attach a new one, and perform some training so it will be able to capture your classes a bit better. And that's the same thing here. We do not have any kind of classes no longer. Here the problem is we don't want to recognize a class. We want to have a data representation, so two objects which are similar in reality will be also similar in those embedding space using a specific distance function. And that's the thing. But I would agree that transfer learning doesn't require any training, because, well, it doesn't require any training only if we recognize the same object, the same classes. But if you wanted to adapt to a different domain, then you would still need to make that training effort, and also provide a huge data set. Okay, how would you optimize the similarity comparison to find outliers? Comparing every point with the other is computationally demanding with large data. Yeah, that's a good point. Definitely, that's an issue if we want to calculate the distance matrix to all the points. That may be a challenge. That's why we typically suggest to focus on some specific subsets of the data, so we don't need to perform that. But of course, if we want to find some outliers in the whole set, that might be an issue. Actually, it may be also done in a different way. Let's say you have all your embeddings already collected, and if you want to find some outliers, there is also a different approach possible, because you could use any kind of vector database like Qdrant, and just simply try to calculate the distance of every single point you have in a collection to some different points. And the idea here is that a point which is an outlier should have the closest point quite far from it. But if the points distances are quite low, then it may indicate there is some sort of cluster in your data. So the outlier should be further away, far away from the closest points. So that might be also a valid approach. And if you have a vector database that is already optimized, since this is in a nutshell a nearest neighbor search by the approximate one, so the distance won't be calculated thanks to HNSW graphs, you will be able to find the closest points with the distance quite easily. So that will no longer require to calculate the distance matrix. Hope that answers the question. How is the anchor selected for Archon-based similarity measure? So there is one thing: if you want to encode the category name, then this is already an anchor. We want to capture the points which are not close to the category name, which have encodings that are not close to the category name encoding, and that's the anchor already. But with diversity search, we just either choose it randomly or select a point which is, well, there might be some rules we can apply. Actually, it's quite hard to tell me like an exact way of how to select it, but basically this might be also selected randomly, because the assumption is that our outliers should be far away from every single item from the data set which is not the outlier. Okay, so not sure if this is the space to ask this question, but I'm interested to know the difference between Qdrant comparing to Milvus. Actually, both Qdrant and Milvus are vector databases. I'm not an expert in Milvus, I have to say that, but we did some benchmarks which are available on our website. So if you want to check the numbers, then that may be obvious what is the difference in terms of performance. From my point of view, using Qdrant with some additional metadata stored for every single vector is way more is way efficient in Qdrant comparing to Milvus. But this is just my experience. I'm not an expert, as already said. But if you want to discuss that, please just feel free to reach me out. We can try to do some detailed comparison. But in a nutshell, Qdrant and Milvus solve the same problem. And that was the last question. One thing that I would like to demonstrate, actually, just put a link to the demo. There are various strategies of how to calculate how to check the quality of the data, how to find the outliers. So we prepared a demo app when you can choose some different approaches. This is actually built on the same data set I was presenting. So you can choose a different approach, either using the name of the item and its image, or the image without the name, etc. There are various ways. And if you just go to the link I provided, you can simply recognize that depending on the strategy you decide to use, there will be some different outliers found out. So basically, if you want to perform that process on your own, then just applying different pipelines might be a way to go to recognize all the outliers, or majority of outliers that you may find in your data sets. Just encourage you to go and find out how it looks like depending on the strategy. And thank you very much.